Hello, welcome to this series of lectures on gravitation. I am Professor Nazir Tantray and I am going to deliver a series of lectures on gravitation and how to solve the problems on gravitation. Basically, it's a lecture series on how to solve the problems on gravitation. But before I discuss the problems, I must give you a small summary of the gravitation. The gravitation is basically the force between any two bodies in the universe. The force between any two bodies in the universe, suppose we have mass m1 and we have mass m2. These two bodies attract each other. And the force of attraction between these two bodies was given by Newton. And the force of attraction between these two bodies is given by F G m1 m2 by r square, where r is the distance between the two bodies. m1 and m2 are the masses of these two bodies. The gravitational force is always attractive. The gravitational force is always attractive and is along the line joining the two masses. G is called the universal gravitational constant. It is universal gravitational constant. And its value is very small, that is 6.67 into 10 raised to power minus 11 Newton meter square per kg square. Its value is very small. That is why the gravitational force between any two bodies is extremely small. The gravitational force is the weakest possible force in the universe. If you have a body of mass capital M of radius r, and you have a body of mass small m on its surface, then the force between this body and this small body is given by F is equal to G m small m by r square. If the body is within the bigger body, that is, if we have a big body here of mass capital M and we have a small body here inside, in that case the gravitational force is different. The law becomes different, and the force is given by F is equal to G m small m by r cube small r. Here r is less than or equal to capital R. The gravitational force between the two bodies creates a gravitational potential energy. The gravitational potential energy is given by the formula that I will give you. Suppose you have two bodies of mass m1 and m2, and we want to know what the potential energy of these two bodies together. The potential energy of these two bodies is given by G minus, it is U minus G m1 m2 by r only, distance between the two, where the gravitational force creates potential energy, and this potential energy is negative, because as you must know, all the attractive forces create negative potential energy. I must write it down. All the attractive forces create negative potential energy. Negative potential energy. Now, the acceleration caused by this gravitational force, the acceleration created by this gravitational force can be obtained as follows. Suppose we have here is our Earth of mass capital M, and here we want to find the gravitational acceleration G at a distance r from the center. First of all, the direction of the gravitational acceleration is towards the center of the Earth. This is just the direction, but we want to know the magnitude of the acceleration due to gravity. The magnitude of acceleration due to gravity is just the force divided by the mass. The force created by the Earth and mass of this object placed here. So first of all, let me find the force on an object placed here at this point. So the force on that mass is F G m small m by r square. In order to find the acceleration of this mass point, I had to divide by this mass. So acceleration due to gravity at any point r. So I will write r here. It is just giving the notation that I am finding the acceleration due to gravity at a distance small r from the center is G capital M small m by r square divided by m. This cancels with it Gm by r square. Here I must write r is greater equal to capital R. because this is the formula which is valid on the surface of the earth or outside the surface of the earth. But if you go within the earth, the acceleration due to gravity may have a different formula. It may have a different formula. So this formula you must remember, r greater equal to capital R. This is the very important formula which must be used when you have the object outside the earth. But suppose you have an object inside the earth. So what is the acceleration due to gravity in that case? The acceleration due to gravity in case when the object is not here, it is well inside the earth, or it may be on the surface of the earth. So first of all, let me tell you what is the acceleration due to gravity when the object is placed on the surface of the earth. When the object is placed here at this place, so what is the acceleration due to gravity? So acceleration due to gravity on the surface of the earth, just on the surface of the earth, let me denote by g, is gm small m by r square divided by small m. So this cancels, so you have g of gm by r square. This is the formula for acceleration due to gravity on the surface of the earth. But now only case that remains is what is the acceleration due to gravity if you go inside the earth? If you go here, somewhere here, what is the acceleration due to gravity here? So as I have to deal only with the problems, therefore I just give you the same summary of all these things. I don't derive anything. So I must just write down the formula. So what is the formula that I have to write here when you are well inside the earth? The acceleration due to gravity well inside the earth, again I will write r here because it is anyway r distant from the center. It is gm by r cube small r, where r is less equal to capital R. If you want to check this by the boundary conditions, you just put r small r is equal to capital R, put it here, it will be again gm by r square. So this is the formula which is even good on the surface of the earth. So when you place small r is equal to capital R, you are getting the same formula as you had on the surface of the earth. But again, using this formula, if you want to find what is the acceleration due to gravity at the center of the earth, so what is the substitution that you have to make for r? The substitution that you have to make for r is 0, because you are going at the center of the earth. It is 0 and the acceleration due to gravity at the center of the earth becomes 0. So it is very obvious that the acceleration due to gravity at the center of the earth is 0. I must write the statement here. The acceleration due to gravity at the center of the earth is 0. That you must remember. Okay, let me go to a few more examples. What is the potential energy if a particle of mass m is placed on the surface of the earth? The potential energy of an object when it is placed on the surface of the earth is given by, it is the shape of the earth, it is the object of mass m, obviously this is the distance r, it is the center, and mass of the earth, let me suppose it is capital M. What is the formula for potential energy of the system of the earth and the mass placed on the surface of the earth? The potential energy is given by the rule U is equal to minus G capital M small m by r. If the object is well outside there, somewhere here, then the formula is minus G capital M small m by r, where r is greater equal to capital R. The formula can work even if r is equal to capital R. So somewhere you are here. But if the object is inside the earth, not at the center, inside the earth, in that case, what is the potential energy of this object with respect to the whole earth? So formula is absolutely different. So the formula in that case is U is equal to minus 3 by 2 mgr plus 1 by 2 mg small r square. Here I should write capital R. So this is the formula for potential energy anywhere inside the earth, where r is less equal to capital R. This is the potential energy of an object which is placed anywhere inside the earth. If you want to check the formula, you place this small r is equal to capital R. If you place this small r is equal to capital R, you must get the same rule, same formula as that on the surface, because you already know what is the potential energy on the surface of the earth. If you put this small r is equal to R, let me put it like that. In this formula, if R is equal to capital R, if R is equal to capital R, so I must know, if I place R is equal to capital R, I want to know what is the potential energy inside the earth, on the surface of the earth, because if you put R is equal to capital R, you are just getting the potential energy on the surface of the earth. So let me see what is that potential energy. That must be same thing as this. After all, I am putting it into the boundary condition. So when small r is equal to capital R, I must get U is equal to minus 3 by 2 mgr plus 1 by 2r mg capital R square. So you cut it like this, and then U is equal to minus 3 by 2, 1 by 2. It is, if you, what you call as, you simplify this, it is minus mgr. And now if I substitute is g of the earth, g on the surface of the earth, so U is equal to minus m, it is gm by r square into r. So this cancels with this, it is minus g capital M small m by r. So you got the same result. So this is the correct formula when we are inside the earth. So it is the potential energy of any object well inside the earth. So what is the potential energy at the center of the earth? So for that, what you had to substitute for small r? You had to substitute for small r 0, because that will make you at the center of the earth. So if I substitute for small r just 0, I must get U is equal to minus 3 by 2 mg r. So potential energy at the center of the earth is minus 3 by 2 mg r. Minus 3 by 2 mg r. So potential energy at the center of the earth is minus 3 by 2 mg r. So that is something like this. So if you put small r is equal to capital R, it is minus 3 by 2 mg r. If you substitute for g, so it is minus 3 by 2 m g capital M by r square into r. This cancels with this. It is minus 3 by 2 g capital M small m by r. This is also the formula which you can remember. So this is all about the potential energy. And I must give you general features of the gravitational field. As we all know that gravitational field is a conservative field. Conservative field has certain properties. I want to write down the properties of general conservative fields, and gravitational force is also a conservative field. So in conservative fields, the total mechanical energy in the given conservative field remains constant. I must write down it. The total mechanical energy in the conservative field remains constant. And as we know that gravitational field is a conservative field. The total mechanical energy in this field remains constant. That is, if you release an object from certain height, it has got a highest potential energy. But the moment you release it, the potential energy continuously converts into kinetic energy. But the sum of the two energies always remains constant. When the object hits the ground, it hits the ground with the largest kinetic energy. But by the time it reaches the ground, its potential energy is already 0, which we define, if we define potential energy on the surface of the earth as 0. So the total mechanical energy always remains constant in the given conservative field, and gravitational field is a conservative field. And the property of all the conservative fields is the force and potential energy are related. The force is a derivative of potential energy. It is a general property of a conservative field. That is, we can write force conservative. You can write it. You can say it's a conservative force, or for that matter, it can be gravitational force. It is also good to write in case of electric field, because electric field is also a conservative field. So, conservative field force is the derivative of potential energy. That is minus du by dr. This is a formula that if you are given the potential energy, from that potential energy you can find out the force. If you are given the force, you can find the potential energy. That is, you see, I can invert the formula. I can write the formula in the integral form. So you see, I can write u as a function of f. In other words, I can write u is equal to minus integration of f. or for that matter, if you put the formula in a more generalized manner, potential energy at position 2 minus potential energy at position 1 is equal to minus of, say, from position 1 to position 2, F dot dr. This is more general formula which you must remember to solve problems. And what about the gravitational potential? Gravitational potential is it is just the potential energy per unit mass. It is just the potential energy per unit mass, or it can even be defined what's the work done per unit mass in getting the mass from infinity to the present position in the given field. I will repeat, it is the work done per unit mass in getting the mass point from infinity to the present position in the given field. So I can find the potential difference between the 2 points in the given gravitational field as this. We already know, although I am avoiding the derivations, but sometimes it becomes very important to have little derivations. So u2 minus u1 is equal to minus F dot dr. F dot dr. So it is from 1 to 2. Now this is the potential energy when the mass is placed at position 2. So I can write it, it is m, mass of the object, into potential there at that position, minus m, it is the potential at the position first. So minus 1 to 2 F dot, F is the gravitational force, then you can write mg dot dr. This m can be taken as common here, so it is v2 minus v1, it is minus 1 to 2, m you can take out, m you can take out, it is g dot dr. So this m gets cancelled here, so it is v2 minus v1 minus 1 to 2 g dot dr. This is the formula for finding the potential energy difference in the given gravitational field. So I will write it down. This is the potential difference between 2 points in the given gravitational field, Although this equation can be inverted and written that way, acceleration due to gravity can be written as, if I invert this equation, doing a little more steps, and I can convert it back, so I can write acceleration due to gravity is derivative of the gravitational potential. Basically it is the same formula as this, F equal to minus du by dr. It is just, I replace F by g and u by gravitational potential. If you simply put F is equal to mg here and u is equal to potential into mass, and you will get the equation. So it's very easy to convert this equation to this equation. These are few things that I have discussed with you. Keeping these things in your mind, I must go to some problems. And the source of problems, the best book that I recommend to you people who want to prepare for IIT, who want to prepare for other competitive examinations, that is S.C. Verma is a good book. So I'll be getting the problems from S.C. Verma and solving them for you in this lecture series. So let me go to the problems of S.C. Verma. Problem number 1. I will start with simple problems, but later I will end up with most difficult or most tedious problems, but I have to start with simpler problems. The first problem that is here with me is 2 masses of 10 kg each or at a distance of 10 centimeters. First of all, the force between the 2 masses is attractive, that you know, because gravitational force is always attractive. Gravitational force is always attractive, and it's always along the line joining the 2 masses, centers of the 2 masses. This is the direction of the force. And if I want to find what's the force between these 2 masses, what's the force on this mass, or what's the force on this mass, of course these forces are mutual. Whatever force is on this mass, the same amount of force on this mass. So I must write down the equation. The force is equal to G m1 m2 by r square. This is the formula that we already know. Substituting the values, so that is F is equal to 6.67 into 10 raised to the power minus 11 into m1 10 into m2 10, and r square 10 centimeter and 10 to 10 raised to the power minus 2, that will make it meters whole square, and this will give you the answer. Very simple problem. So you copy this problem and I will go to the next one. So problem number 2. 4 particles having mass m, 2m, 3m and 4m. I have 4 particles which are placed on the corners of a square. This is mass m, this mass 2m, this mass 3m, this is mass 4m. And now what we have to do, the question asks is, find the gravitational force in a particle of mass m placed at the center. I have to find the force. Due to these 4 masses, I have to find the force on a mass placed at the center. Mass placed at the center. I have to find the force on this. The distance between the two, the edge of the square is A. It's A, this is A, this is A, this is A. And this distance is, if it is A, it is A root 2 divided by 2, this is A by root 2. It's A by root 2. I want to find force on this. The force on this mass due to this 3m is in this direction. Due to this mass is opposite to this direction. It will attract it in its own direction. This 2m will attract its own direction. So I have to find the net force. The net force is, let me take this as the x-axis and this as the y-axis, or you may keep it y-axis and this as x-axis. Can you tell me what is the net force along the x-axis? The net force along the x-axis, Fx, is equal to, that is the force due to this minus force due to this. The force due to this is g 2m into m by what you call as this distance square. This distance square, that's a by root 2, a by root 2 whole square. This is the force due to this 2m mass on this object minus the force due to 4m mass, that is minus g, that is 4m into m by a by root 2 whole square. Now what is the force in this direction, in the y direction? So that is Fy equal to, that you write as g, it is 3m into this m divided by this distance square, that is a by root 2 whole square, minus this force, because this force minus this force is the net force in the y direction. So it is g m, this one, into m by a by root 2 whole square. These are the two forces in two directions, the x direction, y direction, and you know the angle between them is 90. So finally you have to find the net force. Fx and Fy, you have to find the net force of these two forces. But first of all, we have to simplify. The simplification of Fx and Fy reduces to, the simplification gives us Fx is equal to, g will be taken out, 2 will be taken out, this 2 will go up and will taken out, and a square will come out. It is what you call as 2m square, this one, minus 4m square. That will give you minus 4g m square by a square. Have a look. It is 2, 4 with a negative sign, of course, because it's more, g m square by a square. What about Fy? Fy equal to, it is 2g by a square, again 2g by a square. Inside it is 3m square minus m square, 3m square minus m square by, no, so it is what you call as 2g by a square into 2m square, that's again 4g by a square into m square, of course. If you put it equal to, suppose a, it is also equal to a in terms of magnitude. So what is the resultant of these two forces? Because fx and fy have the same magnitude. So what is the resultant of these two forces? The resultant of these two forces is f equal to root of fx square plus fy square is equal to. So it is root of a square plus a square. I want to simplify it that way. By substituting directly, it will become a little complicated. So what I do is that I will put it a square, I will put it a square, so it will be f equal to a root 2. So a I will substitute, that is 4g m square by a square root 2 should be the answer. So it is the net force on that mass which is placed at the center of the square. And the square is, on the square we have 4 masses given by m, 2m, 3m and 4m. Let me go to problem number 3. 3 equal masses m are placed at the 3 corners of an equilateral triangle of side A. Find the force exerted by the system on another particle of mass m placed at the midpoint of the side at the center of the triangle. Third problem is, suppose the problem asks that if you have three particles at the 3 corners of an equilateral triangle, and each side is A, and the masses of the particles are m each. And the question is, if I place one more mass, that is if I place a mass on any side of the triangle, so what is the force on that mass? So let me place the mass over here. Its mass is m. You know, as the triangle is equilateral triangle is 60 degrees, it is 60 degrees, it is 60 degrees again. So what I need to know is this distance. So if I make this a vector A, this vector has got this much of horizontal component, that is A cos 60, and this much of vertical component, that is A sin 60. That if you want to do it is A or root 3 by 2. As you must be knowing what is the sin 60 equal to, root 3 by 2. So here I want to find the force on this object. The symmetry demands that the force due to this and due to this must cancel out. The force due to this and this must cancel out because they are on the other opposite sides. They will attract the particle in their own towards its own direction. So this is the force due to this mass, and this is the force due to this mass, and these two forces cancel out. When these two forces cancel out, the only mass remains which attracts the body is this mass. So this is the force in the upward direction. So what is the force in the upward direction now? The force in the upward direction must be, you know, this is m, and this is m also. So force should be simply g m into m square, because you know these two masses cancel out the forces, and this mass pulls it upwards, that is m square by, for the distance, that is a root 3 by 2 square of it. If we use the formula, the general formula, the gravitational formula, f is equal to g m1 m2 by r square. So if you simplify this equation, it becomes very simple. F is equal to g m square by a square 3 by 4. 4 will go up. So it is 4g m square by 3a square is the answer. This is the answer. So again, in the same question it is asked that if you place this mass point not here but at the center, so in that case what is the force on that mass point? So we had to see to that. So if you place the object at the center of the triangle, what is the force on the mass placed at the center in that case? So let me put it this way. It is the triangle again with the mass point on the corners, and here is the center. Again I have the mass here m. It is mass m here. So it's m and m. It attracts it this way. This mass attracts it through gravitational force towards its own self. So this mass will attract it upwards. this mass will attract it like this. So these are the three forces in the same plane. If the three forces are in the same plane and the angle between two forces is 120 degrees, they will cancel out. So the answer must be simply 0. F is equal to 0. So if you place a mass at the center of the triangle, equilateral triangle, the net force on that will be 0. But I want to demonstrate that. But here I just told you that if there are three forces and at an angle of 120 degrees and these three forces are in the same plane, for that matter any three vectors having the same magnitude or in the same plane having the angle between any two vectors 120 degrees, the net vector will become 0. The magnitude of the net vector will become 0. So let me demonstrate that a little more. So if you have, this is the force F upward, this is the force again F, the same magnitude because same distance, same masses, so same magnitude. So this is the force again F. So these are the three forces. These three forces are at an angle of 120, 120, 120, 120. So if I put it downwards like this is 60, this is 60. I want to resolve this into components and this into components. So if I put a line horizontal, so this F will, a component of this F will be F cos 60 and this will be F sin 60. This will be F cos 60. This will be, what to say, sorry, this is F sin 60 of this F. If I resolve this into components, this F will be F cos 60 and this will be F sin 60. These two forces will cancel out anyway because they are opposite. And these two forces, this is F and downward is F cos 60 plus F cos 60, that will make it again F because cos 60 is 1 by 2. So it is F upwards, net F downwards, so cancel out and this force cancel out this force. So the net result will be 0. The net result will be 0. So that means if there is a triangle, equilateral triangle, and mass points are at the corners, and you have a central point and you place a mass point there, the net force on that mass point will be 0 because of the reasons that I have explained you. This was the first lecture that I delivered you on gravity. It was basic, and in the next lectures I'll be doing more problems with you so that this becomes very clear to you all.